Now that we're finally here, we can exhale. Yes. We got and we spent so much time organizing this event that we're finally standing here looking at headlights and wondering what we should tell you.
Look, maybe you know about this event since 1 month, something similar, but we started in January. So it's a long time.
Before that even. So who's heard of Yuri's Night before? Only a couple of hands.
Yeah, a couple of hands.
Okay. So, yeah, I'd never heard of Yuri's Night until I took a zero-G flight in the US. And on the laptop of the flight director, he had this sticker of an astronaut, as far as I was concerned. I said, "What's that?" He said, "That's Yuri's Night." I said, "What's?" Oh, no. Hello? Oh. Yeah, what's Yuri's Night? Oh, this is a worldwide phenomena that we get to celebrate exploration of space, and starting with Yuri Gagarin, that's where the name Yuri's Night has been taken from. And I won't explain too much about Yuri now because Valentina has an entire presentation to tell you, to get you introduced to Yuri Gagarin. So Yuri's Night is basically just a nice reason to celebrate the exploits of human exploration into space. So anyone around the world can organize a Yuri's Night event. And so I met Valentina not so long ago, just at the beginning of the year. She's an amazing astrophysicist. I said, all right, I need her. Let's get together, let's make an event. And so from that, we invited some speakers, and we were very honored with the speakers who said, yes, we would like to join for Yuri's Night. So we're looking forward to entertaining you and informing you and educating you with the presentations. We also have a couple of surprises in store, things that were a little weather dependent, so we didn't announce them earlier because we weren't certain if they could go ahead. But as you've probably all noticed, the ones of you who are sitting down, the priority seats, you all have a little package. This is a rocket pack. This little envelope contains the ingredients that you're going to be using during the break to make the sweetest, cutest little rocket that you've ever seen. And they work. I've tried out dozens.
But pay attention to the glue.
Yes. We can do that before the break.
Okay.
So you'll notice that the ingredients do look rather fragile, but we're going to instruct you how to use them. So sit tight. You don't need to do anything with them now. We'll be using them during the break. That's when we're going to hold a rocket competition. It's a matchstick rocket competition. And that's going to be held outside, but we'll give you more details closer to the break.
Yep.
Okay, so what else? We should thank also KOSMOS for hosting us. They've been very gracious to invite us to have our event here.
Yeah, right, it's there.
Yeah, this is Rito, so thank you
Thank
very,
you.
very, very, very much, Rito. Okay, well, is there anything else we need to introduce before we start? You. I need to introduce Valentina. She's actually the first speaker this evening. The reason is because we wanted you to be familiar with Yuri Gagarin. And so Valentina has a presentation about Yuri Gagarin. So, Valentina, please
Thank you.
take it away.
Thank you so much. Thank you. So thank you also to you for coming here. It's really an honor for me to be the first speaker. I have to say that I'm a bit nervous, never talked with so many people in front of me. But so I want to tell you something more, as Miki said, about the protagonist of our evening, Yuri Gagarin. So first, I would like to ask a question to the audience. So my dream when I was a child, already 8 years old, I wanted to become an astronaut. I wanted there, and I also want now. So is there anyone else who wants to become an astronaut here in the audience? Great. It's great. Yeah. I was expecting the same reply, but, well, for the other people, I cannot believe how it's possible. I mean, it's the best job in the world. You know, there are something like not more than 500 people going to to the space up to now, so not more than 600 astronauts in the world. But this is really cool. So for this reason, when I was a child, I was kind of, oh, I have to know everything about astronauts because I want to become an astronaut and I want to know what makes interesting a person, what allow a person to become an astronaut. So with my presentation, I will talk, of course, also of the mission of Yuri, but I want to tell you something more about him, about his life. So I want to start with the sort of identity card of Yuri Gagarin. This was the membership of Yuri Gagarin in the Soviet Union. So Yuri Alexeyevich Gagarin, pronunciation should be correct because I asked two Russian friends to correct my Russian pronunciation. So he was born in the 34, before the Second World War, in a small village close to Moscow, about 200 kilometers on the southwest. The name is Klushino. And he was born in a very poor family. So both his parents worked in a collective farm. And I like to say that his distinguished features already as a child was a passion for flying. But why? Because he lived during the Second World War. His childhood was in that period. And he was used to see a lot of fighter pilots in his village. But he didn't study to become an astronaut at the beginning. So this is what he studied. In the 50s, he did an apprenticeship as a foundryman. And then he went to the Industrial Technical School in Saratov. And there he decided to attend the local flying club. And that was the decision who completely changed his life, because he was really good at flying. And someone noticed this, and he was selected from the Soviet Air Force to join the first real pilot school. So after 2 years, in the 57, he became a lieutenant in the Soviet Air Force, and he was sent to Murmansk Oblast. This is, I put that is in the Norway border because I thought, well, maybe people don't know, you know. And the problem with the Norway border is that it's very close to the Arctic Pole, and the weather is terrible. It's terrible condition for flying, it's very risky. But for him, it was kind of additional training because he was really good. And you know, in the 59, something happened. So basically, there was a staff of doctors, of medical doctors and psychologists, going around the different air bases in Russia and looking for very special person. They want to have special fighter pilots. They don't say for what reason. They just go to different air bases and check with different tests which want to experiment with the psychological and physical endurance of these pilots, without saying for what. We now know that they were selected to become candidate cosmonauts, but they didn't know at that time. And then Gagarin was selected with other 19 pilots, and he was moved from the cold Norway border to Moscow, just outside Moscow, in a place that now is called Star City. The name is already programmed, but it's where the Cosmonaut Training Center is now. At that moment, they still didn't know why they are there and for what reason they are trained. I will not have time to tell you more about how was the training for a cosmonaut at that time, but I can cite something like isolation chamber, centrifuge, or other stuff really crazy. If you want, you can ask me later because it's really interesting. But I want to tell you, I want to show this evaluation that was written by a Soviet Air Force doctor about Gagarin, because I think it's nice to notice that he was considered a modest person with a fantastic memory, with a sharp sense of attention, quick reaction, a persevering person, and still very good in mathematics, in higher mathematics. So for the people who want to become an astronaut, just take note of this because it's really important. I'm already there, and I'm also modest, as you can notice. So, but the point was, why are they, this staff of doctors, going around Russia and looking for different, for very special person? Because you probably know, at the end of the Second World War, there was also the so-called Cold War between the Soviet Union and the United States. And what happens is that this competition also moved to the space, and they want to show to the others that they have the supremacy, they have the power also in the technology. And the Soviet Union was already really ahead in that moment, because in the 57, they were already successful in sending the first satellite, the Sputnik 1. And they also sent the first living being, the dog Laika, on the Sputnik 2. Well, in that moment, the United States was not very good in this. The first satellite, the Vanguard, failed at the launch. It exploded at launch. And then they also do 12 tentatives to send the first satellite. As you say, I wrote Discovery 113 because only the 13 was successful. And despite the name, don't think that was a research satellite as they want to show. It was a spy satellite in reality. But at the same time, in the 59, you can see Luna 1, 2, and 3. They were mission to send to take information about the moon. And with the Luna 3, they also got images, the Russian, from the dark side of the moon. So they were really, really good. And in the 61, they sent the first man in orbit with the Vostok. So the Vostok 1, I just want to show you the size. This is the entire size of the rockets. But what I want that you notice is that the Vostok, the spacecraft, is really small. So I don't discuss the rockets because we have a space engineer here around. So she will tell you something more. But what I want to discuss is the spacecraft, the Vostok real. So as you can see, there are two parts, two modules. The lower part is called the instrumental or service module, and the upper part is called spherical or re-entry module, where Gagarin was seated in a not very comfortable position, also because you have to think that is only the diameter of this sphere is about 2 meters and 30, not more. So not enough space, but the Gagarin was quite short, 1 meter and 57, so maybe it was still good for him. The other things that I want you to notice, because it will be important later, is that the two models are linked by some cables, and maybe you can see it here. And this will be really important later, but before talking of his journey, I would like to tell you something more. So it was really a risk mission, this one, really dangerous. And there are a lot of safety measures taken. And one, for example, was that, inside the spherical module, there was food and water for 10 days. It was supposed to last only less than 2 hours, but in case the retro rocket's engine that was here would not work, well, the problem is that they have to wait at least 10 days that he naturally come back to Earth. And the other problem was that poor Gagarin, he was put on a higher orbit compared to the calculation, and he would need something like 20, 30 days to come back to Earth. So it was really a lucky guy, I would say. And the other things I would like to say is that Gagarin, despite he was a very good pilot, he didn't have any kind of command in this mission. Everything was controlled on the Earth. So the doctors were not sure about the effect of gravity, of the effect of the free fall, the diminishing of the gravity on the body and on the mind. They say, oh, maybe Gagarin can lose his consciousness. Maybe he's not able to come on the Vostok. So we have to do everything from Earth. But of course, also Yuri knew that the mission was very dangerous. But another features of astronauts, I would say, that is that they are a very brave person. So it say that nothing will stop us. The road to the star is steep and dangerous, but we are not afraid. And this is something that I really like because it shows the braveness of this person. But Gagarin was not only a brave person. I would say that it's important to explore also his human side. And the point is that he was a man like us. And he has a family. He was married with a young girl called Valentina, like me. And, he has already 2 daughters. The first was Galina, and the second, Yelena. And, his family didn't know anything about this mission. So he wrote them a letter to tell them in case something went wrong. So this is just a short summary, a short part, but I want to show you. So he said, today a governmental commission decided to send me first to space. So again, they didn't know anything. He just went out, so see you this evening, and instead. And And then I like to show that he really trusts what they were doing. He said, I trust the hardware completely. It will not fail. But then he was also a normal person. He know that accident may happen. And if at the end he said, life is life, and nobody is safe from being run over by a car. You know, it's something that I usually say to my parents when I have to take a flight, because my parents are always, oh, attention, pay attention, because it's very dangerous. Yeah, also going to the street. And sorry, I'm not Swiss. I think you can already understand from my accent that I'm British, of course. So I'm Italian, and I can assure you that the streets are really dangerous in Italy. So, but what happened on the 12th April of the 61? So, Gagarin was not in Baikonur, as many people know, because Baikonur was a bit far away, but Russia wants to keep secret this place. It was instead a stepan in the Eurasian place. The code was Tiara Tam or something similar. But the point is that it is in Kazakhstan, in the actual Kazakhstan, and he woke up at 5:30, very early. He had an early, so woke up, he did his exercise, and he had breakfast, already meat for breakfast, very Russian breakfast. And then he went on a bus. Here you can see it. This is a movie that is free. You can find online. It's called First Orbit, and you can see how he arrived by bus to the place, to the launch pad, and he sat in his spherical capsule module. And what I found now, as I read, is that he had 64 heartbeats per minute before the launch, just 30 minutes before. And I find this really exciting because I'm sure that I have more at the moment. But there was another person that had more beats per minute at that moment, and was Korolev. Korolev was the supervisor engineer who projected everything, who designed the mission. And he was more nervous than Gagarin. He was forced to take a pill for his heart. And I cannot believe, to be honest, this, because he was the person going up there, not Korolev. And another funny thing that I want to tell you is what cosmonauts still do now to remember basically Gagarin. So you know there are some traditions, and basically Gagarin decided to not watch the rollout of the rockets. And nowadays the cosmonauts do the same. They don't watch the rollout. They instead have an haircut 2 days before, like Gagarin did. And they also have drink a glass of champagne in the morning. Good, maybe it's also part of the breakfast, Russian breakfast. And they sign the hotel room door. This is something that is done from old astronauts, also from American astronauts. And what is very nice is that they have to be a mandatory break for bathroom, to pee on the bus tire who bring them to the launch pad. This was something that Gagarin did, and then now they continue to do, to keep the tradition, and you know, maybe it's also good luck. And yes, also women, if you're wondering. So, what happened at the moment? Look, last check, everything is fine. Let's check with the basis. This is still in the First Orbit movie that you can see for entire. And 9 and 7, Поехали. So Поехали is the Russian word for let's go, because Yuri Gagarin was really so excited, like probably I could be also, because he was the first. He was the first person who did an entire orbit around our Earth. Can you believe being up there and see our planet like a small blue pearl in the black sky? And he was able to see everything, really everything. So the rivers, the clouds, to distinguish oceans, deserts. He was in continuous contact by radio with the Earth. And if you look at the first orbits, there is also the registration of what he said. And it's great because he's always kind of, I'm fine, everything is fine, don't worry. How are you? He was also very humor person, how are you? He was up there, 300 kilometers, and he was worrying about the others. And everything went quite smooth, I would say. But the problem started when he started to come back to the Earth. So it was 25, so already 1 hour passed. And first problem was was fine. So the retro rockets, you remember, I say, well, if retro rockets didn't work, then he has to come back in 10 days, probably more. But everything was fine. The problem was, you remember the cables? I said to you, the two modules are linked with cables. The problem was that the re-entry module didn't detach from the service module. And this was a problem because this stuff remained detached together, and it was not designed, the instrumental module, to come back to Earth. And therefore, this provoked some strong gyrations. He said something in his book, on the Road to the Stars. He wrote, it was head and feet, head and feet. Now I see the desert, now I see the sky. Because it was really 10 minutes, probably very scary. But luckily, these cables broke due to the friction with the atmosphere. I already told you, he was really a lucky guy. And the edge of the spacecraft was released. You remember, everything was automated from Earth, and it was still at 7 kilometers. Then he was ejected, everything fine, and he landed with his parachute and arrived to the Earth at 10:55. And this is the end, instead, of the Vostok, of the spherical model. Inside this stuff, it would have died, but the problem is that Gagarin was also forced to lie for basically 10 days because, I want to just summarize the main number for this mission. So for me, Yuri Gagarin is not only the first man into space, is the record man, because he was the first to reach this velocity. Who can see also now, this 27,000 kilometers per hour. And in 108 minutes, he did an entire orbit around our Earth, and they reached a maximum altitude of 327 kilometers. And so this was a record that this federation, my French is worse than my Russian, but this federation just decided to register the record. But the point, the record in altitude, I mean, but the point is that it was not a real record according to their rules, because they want that Gagarin, that every pilot remain inside the spacecraft for register the record. And can you imagine if he was still inside of that stuff? So for me, it's kind of crazy because Gagarin was forced to lie, of course, on this, but I mean, it's the man of record. He not only opened the space doors, but I mean, he was the only person. Can you imagine? He saw desert and oceans and all the continents just in 108 minutes. It's already this a record, right? So of course, the news was in every journal the day after. It was a secret at the beginning, but not once everything worked, right? So it was in Russian newspapers, but also in France, in Germany, in Italy, in Spain, and also America knew this. So they were, can you imagine these poor Americans? So they were thinking, oh my God, we were sleeping. And Soviets put a person on orbit. So the space race basically continued, as you know, and ended at the end in '69 with Neil Armstrong and Buzz Aldrin on the moon. I don't want to discuss all the steps in between. But what I'm really happy to say is that nowadays we don't have any more space race. We have space collaboration, I will say. I like one definition that I heard once by Claude. The space brings people together, brings nations together. And on the International Space Station, they work all together. And I would like also to remember you that this is not our Milky Way, this is Andromeda, but it's the most similar galaxy to ours. And I would like to remember you that we are just a point there. So there is so much to explore yet that we have really to thank Gagarin for his first mission, for his brave. And I also want to thank you, of course, for the attention and the patience before. Thank you so much.
Thanks, Valentina. So you mentioned these traditions of Yuri, and seeing as we have an astronaut here, I'm curious to know, you don't have to answer if you want to admit to peeing on the back of a bus. But Claude, do you follow the same traditions that Valentina mentioned? Yes? All of them? He says, yes, all of them.
That's true.
Oh, awesome. He'll tell us about it later. Okay, so yeah, thank you. I was reading a lot about Gagarin, of course, for the event, but you illuminated a lot of little pieces that I also didn't know about. So, yeah, so I guess we'll move on with the next speaker. And actually, before we move on, if anybody wants to know more about Gagarin, ask Valentina, because I know that she knows way more than what she was able to pack into this presentation.
Of course, of course. I will be here.
Okay.
Thank you so much.
Yeah, would you mind setting up for Kamleshwuree? So the next speaker that we have, actually, we didn't mention what the schedule for the evening is. We have a few speakers, and then we'll have a break in the middle at the same time as the competition. And then we have some more speakers. Speaking of more, that's one of our surprises. We have Professor Ben Moore, who's also joining us this evening. And so at the end, we will have a closing of the event, but then we'll continue a little further with Ben Moore speaking with Claude Nicollier, just to continue. So you're very welcome to stay on Shoot the Breeze with, with an astronaut and an astrophysicist. So I guess now I'll introduce Kamlesh to the stage. So Kamlesh belongs to the Swiss Space Office. There's a Swiss Space Center, but she's from the Swiss Space Office. And actually, when I asked Kamlesh about this, she said, well, actually, I'm a lawyer. I said, okay, so how does this work with space? And she about, well, how does it work up in space with the law? I said, yeah, so like, for example, if an astronaut on the ISS, the International Space Station, chooses to shoot and kill somebody, which country takes care of that? And Kamlesh explained to me that, well, actually, the ISS has its own agreement, and it's amazing. You basically describe something that the way the things are working with the law up in the space is like humanity's best step forward. If we could take a piece of how they're operating up in space and operate that way down on Earth, the world would be a better place for it. So please come and tell us more. Okay. So, Kamlesh Brocard.
Thank you, Mickey. So, that is on, yeah? Okay. So, good evening, everyone, and thank you very much for being here with us on Yuri's night. Actually, I will admit something. When the organizers contacted me and asked me to speak at the event, I thought, oh, do they know I'm a lawyer? It turned out they did. And that was also part of the reason I was invited. So I am from the Swiss Space Office, which is part of, so just bear with me on this. It's part of the State Secretariat for Education, Research and Innovation. It is a federal office. What I will share with you will likely be a bit less lively than what Valentina had to say, but I shall do my best. And first of all, we will go into the details of space law. Okay, not quite what I was expecting, but we'll do this. I'll start off with a really snapshot of the international legal context. I'll follow on with an overview of space in Switzerland, what really is meant by it, and I'll carry on then with a quick peek into opportunities, for example, careers. So I like also to talk about that because one of my roles at the Swiss Space Office is promotion of education as much as I can. So without much ado, space law. So context. Valentina touched on it. So we're talking about a body of law of international conventions. Okay, see, I don't work with technology very often, so thank you, Mickey. The international setting, and why was it that there was a need for a legal regime? I mean, what's up there to need a legal regime? I read somewhere, and this is not from me, I read it and it sticks with me. And somebody said, when men and women were dreaming about reaching for the stars, some people reached for their law books. They were not wrong. The first group wasn't wrong, the second group wasn't wrong, because in 1957, the United Nations brought up a group together. It was a committee that was designated to discuss peaceful uses of outer space. Remember, we're talking about 1957, Cold War. Cold War also brought Yuri Gagarin into space. It also brought the first man on the moon. However, Cold War also meant that the then only two spacefaring nations didn't want the other one to be there first. So what they did was, they managed to bring up the committee, which was called the Committee for the Peaceful Uses of Outer Space, KOSMOS, is the United Nations Committee, and it's still running, it's still very active. To date, there's about 80 countries that's members of the KOSMOS. Came together in 1957, and in 1967, 10 years later, they had brought out and ratified about the 5 main conventions. That is, at any point in time, a world record, if you're looking for records in space. It doesn't happen. It just doesn't happen. You get 5 international conventions ratified by states. It did happen. And what it meant was it brought peace to space. I will not go into the details of all the documents. You can find it on the United Nations website. You Google space law, you'll get everything. These are the main elements. Space is free for all nations to explore and sovereign. Claims cannot be made. If any of you has ever bought a piece of the moon, sorry. Nuclear weapons, other weapons, mass destruction not allowed in Earth orbit, celestial bodies, or elsewhere. Peace, supposedly. Number 3, it's individual nations, states, that are responsible for any damage the space object cause. It's the individual nations who are always responsible on the international level. Don't go saying I gave you any ideas. The state is responsible. Let's leave it at that. Now, that was my snapshot on the legal context. It's a very fascinating area. Just reading the stuff it brings you a lot more of the context that it was all done with. Go and read it if you fancy it, but it's interesting. I'll now move on to space in Switzerland and how and whether and why does Switzerland get involved in space activities? What's in it for us? I still do get questions about, really? What do we do? What have we got to do? Let's have a look. That's where we are. That's us here. I have left it in German because it's so cool that I can use all 3 words starting with an N. So, we do it. We actually engage in space activities because of the applications, because of the curiosity we have as men and women to go and explore and go beyond what we already know, this insatiable need that we have to go beyond. And space is really your ideal playground for that. And Nischen. Nischen is basically, so I'm working for the federal administration, and I also always have in mind, what do I use? I use public funds. I cannot just go and say, oh, that looks like a cool project, let's try and invest. No, we do not do that. We look for things that bring back benefits for us, for our citizens, for the country. And in order to do that, Switzerland's strategy is to invest in the things that we're either already good at or things that we consciously believe, reasonably believe we can be good at. Because it is very often the final frontier. We have to risk things, we have to try things out, but we also need to have a reasonable belief that we will succeed. So that's why we do it. And who do we do it with? So that basically covers everyone in the world. ESA, at the top there, is the European Space Agency. Switzerland doesn't have its own space agency, so everything we do, about 95% of our space budget is invested via ESA. We then have some projects with the European Union, like some projects that we embark on with the European Union, and we're also a member of the United Nations and of the KOSMOS, which is the committee I mentioned earlier. What we do, how we do it, and I just mentioned ESA. One important feature about how ESA functions, so it has 22 member states right now. It started off with 7. Switzerland was one of the founding members in 1975. And it's an intergovernmental organization. It is not an EU organization. It is not part of the EU. In fact, we have 2 member countries, maybe soon 3, who are not EU member states. That's how most of the space projects that happen in Switzerland on the national level, or that has a national component to it, is done via ESA. We also have a certain leeway if there's a particular project that we want to do bilaterally with another country or multilaterally, that's also possible, but to a much lesser extent. The ISS, we contribute to the ISS, we're part of it. And there is much more. When I say much more here, I count everything from student projects, I consider maybe research pieces that we do. More often it's with ESA, but it's still not mission specific. It doesn't always have to be mission specific, but it can be at the very start when there's a potential for it to integrate a mission later on. So that's also. I could have added a lot more logos. I've added of missions, different missions where Switzerland is involved. I've only added InSight there. This one, it's to illustrate the bilateral aspect. InSight is Mars-related NASA mission, and I mention it there because it's very actual. On the 5th of May, the mission is being launched, and there is an instrument with a significant contribution from the ETH on it. So that's why it's there. So, the proof, I haven't been lying, we're there. That's where we are. And, okay, at the very top of it, and I know some other people will talk about it, there is the fairing, so there, which is a bit higher up. That was an example of how we contribute to what we do for the launcher. So without Switzerland, really, no launching because this is Ariane. This is the European launcher, Ariane 5, this one. And the fairing is actually produced not very far from here, in Zurich, Seebach. So that's where we are. Where else? It's really a snapshot, but at the moment there is a launch date. This is KOSMOS. It's a satellite for the characterization of exoplanets. It is an ESA small mission, and it will be launched anytime between end of 2008 and start of 2018 and start of 2019. It is an ESA mission, but under Swiss leadership. In fact, the proposal came for the mission from Switzerland, from the University of Bern, and it was accepted to be implemented by ESA, and so it's really a 50-50 mission. And the University of Bern, Professor Willy Benz is at the head of it, and he is basically, he's doing a lot of the coordination. Sometimes I wonder if it's not more than ESA itself. So that's my part of Swiss patriotism there. Sorry. My next point is, that brings me to the point of the niche that I mentioned to you earlier. So the miniaturization. So Switzerland, I'm not telling you anything new about the miniaturization sector, although working with very small, very high precision products in Switzerland. And you think of the watchmaking industry, and miniaturization is an essential part of developing space activities. There's money involved, right? Just as a rough figure, sending 1 kilogram of weight in orbit, in Earth orbit, cost roughly $20,000, 20,000 US dollars. So anything you can make smaller, that's a win. So in Switzerland, we are very good at it. We've got industry, we've got a legacy of it. The heritage is there, so we do make use of it. My third point here is about technological transfer. There are so many examples I could give you. Right now, even if I try and think of it, it probably won't come to my mind, but technological transfer, especially the automotive and the airplane industry, that's probably the most obvious industries that come to mind when who benefits the most, whose technology, or who can almost readily use the technology that's been developed from scratch for space. But I can also mention, self-heating blankets for newborn or premature babies. Right, there's lots more. Ask me later if you want. I also mentioned earlier that why do we do space? It's got to benefit us all. We cannot use public money if it's only going to benefit a certain sector or a certain group of the population. And I think, I will not go into details of that because it is quite clear. But let's say space applications, space benefits are accessible to all, if not almost all of us, whether it is in our really daily peaceful life and our entertainment, or when we really, really need it, it's there for us. It allows us to save lives, it allows us to gain precious time. It's just there for us. In any modern society these days, you just cannot imagine. We have become so dependent on it, but I don't think we want to do without it either. That's just probably just a cool graphic of, I didn't make it myself, one of my colleagues did, and I thought, I'm stealing that because it's just so relevant, and everywhere I go in Switzerland, it's just, I think it speaks for itself. So I think the season is almost over in most places, but think about that next time you go. I will come to my third point now, which is about opportunities and actors in Switzerland. Probably I'll just finish up on the actors now. So we have in Switzerland, on the more governmental level or para-governmental level, so you have the Swiss Space Office and the Swiss Space Center. The Swiss Space Center it's based in Lausanne at the EPFL, and it's also got an office at the ETH. It was created in 2012 from the Swiss Space Office. Push from the Swiss Space Office because we felt we needed a team, we needed a group that was more on the ground, closer to the community, and not sitting somewhere in an office in Bern. We know what perception that can give sometimes. That's basic. Who's laughing? That can actually really bring us closer and create and consolidate that fantastic community of individual research institutes, individual companies, small companies, medium-sized companies that we have. So the Swiss Space Office is a purely governmental office, and the Swiss Space Center is, we like to call it our right arm because they help us achieve a lot, but they've also got their independent personality. I think I have some colleagues from the Swiss Space Center here. They can tell you a bit more. Does that answer your question, Mickey? Good. Wonderful. Careers, that is my final point, and I will try and give you as much information, but also I'd like to inspire you to go and look further. For people who are looking into future careers, or people who are maybe looking to change careers, we never know. Just, it's worth having a look, I say. That's an ESA production, which calls it, you know, looking for bright minds. They always are. It's always worth looking at what they've got. So, we've heard about the dream job. We've all heard about it. There's not much that I can tell you here, mainly because I do not have several of those qualities that's mentioned there, so I didn't even look into it. Suffice it to say that on that last point, if anyone is interested, ESA does have a periodical campaign when they recruit astronauts. The last one was in 2009, so the next one should be coming in the next couple of years, I should think. So think about it. Oops. Yeah, so you can find out whether you fulfill any of those criteria, and if you do, don't hesitate to contact ESA when the time comes. Again, I think Valentina mentioned some of the tests they had to do about the you know, buoyancy and whether you feel sick or not, that kind of thing, and whether they, you know how to breathe properly when you float. So you can also take the test. However, I know the astronauts are probably the cerise sur le gâteau. They're really the best thing, the best envoys in all sense of the word that we can have for space. And we also have lots of other people who work with them. So we do have the engineers, the development engineers, the mechanics, and the, I'm not sure how to translate that one. But, which leads me on to my next slide. There is a whole lot of them. Look, I've left it in German, but you get an idea, and especially there, look. Somebody highlighted it. Just to say, look out for what you can do. There's lots of, I showed you earlier, there's lots of companies in Switzerland, there's lots of research institutes, so you can also approach them if you need to. It's not easy. By all means, am I saying, oh, you know, there's all the doors open, just walk in and you'll get something. But it's worth a try. So I think I've reached the end of it. Yes, thank you. And if you have any questions, is it now or is it a bit later maybe?
Yeah, I think it's a bit late. Mm-hmm. Yeah. Okay. And but let's thank Kamlesh. Thank you so much. Later. Okay. So if you have questions, Kamlesh will be with us at least for another hour, I think so. Yeah, okay. And thank you for the opportunity. So in 2 years, people sign everything that we cannot apply. Okay, now it's my pleasure to introduce the third speaker. The third speaker is, again, an astrophysicist. And when I arrived, so I did my PhD in astrophysics here in Zurich. And when I first arrived 5 years ago, he was one of the first person I met in the institute. But to be honest, the first was the secretary. That's fine. And well, the second was my boyfriend, because otherwise he would be angry with me. But yeah, so, and I like to remember the moment when I saw him, because he was without shoes, because he's a very sporty person, and he was probably just arrived by cycling, and he was really happy to see a new person. He told me, oh, come with me, I can show you the Z-Box room. And Z-Box was a supercomputer that he, with other people in the institute, set up for us in the Institute for Computational Science to use. And it was really so crazy. It was kind of, look, this is the CPU, this is this, this is this. And for me, it was kind of, what does this with astrophysics? Should I have to use this stuff? So, but he was, so I wanted him for this evening because he can really make people passionate about something they don't know, like me, for computers. So I want to introduce you Professor Joachim Stadel from the Institute of Computational Science, Zurich. So
can you get the slides? Thanks, Valentina. All right. So, yeah, thanks very much for having me here. I'd like to, in honor of the theme tonight, I'd like to start this evening with a great piece of Russian spacefaring technology, the Proton Rocket here. And you can see it's a very impressive piece of technology. It's for our human scale, it's a very fast device. But as you can see, it's compared to the speed of light. Oops, sorry, I'm pushing the wrong button. Oh, yes, yeah, it's a very small fraction of the speed of light. And if we want to extend beyond the solar system, we're going to have to move significantly faster than this. And this is another type of proton, significantly faster. This is the speed of a proton generated by the Large Hadron Collider. It's probably almost the fastest matter that we as humans have been able to create, moving at nearly the speed of light, I think 3 meters a second slower than the speed of light. This is of course a much more useful speed to get around. With this you could easily reach the nearest star, Alpha Centauri, which is 4.2 light years away. So it would be no problem to do at this speed. And there's another great thing about moving at this speed, at this rapid speed, and that is for the cosmonaut, the clock actually runs really much, much slower. And this is a huge advantage because the trip to Alpha Centauri would, for a cosmonaut, it would only appear to her as taking about 5 hours at this speed. So it's still the case that from Earth, it would look to us like it still takes 4.2 years to reach Alpha Centauri. This effect is known as time dilation, and as Carl Sagan said, it's sort of a fountain of youth for space travelers. And but you know, if we're thinking about traveling through the universe, or you know, we have to realize how big the universe actually is. It's a really, really big place. Here you can see the same galaxy that Valentina showed, the Andromeda galaxy. It's about the furthest thing you can see with your naked eye. It's really much further away than the closest star, 2.5 million light years away this time. And even though that seems insurmountable, and if we were to watch that spacecraft, we'd get bored very quickly, but at the LHC proton speed, the cosmonaut would only experience a 1-year trip, which seems kind of reasonable until we consider that this sister galaxy of ours is really just the closest one, and there are things much, much further away. This is the Hubble Ultra Deep Field, where basically the Hubble Space Telescope has looked at a very blank region of sky, and there is only a handful of stars that you can make out here on this picture. The rest are all galaxies, incredibly far away galaxies. So the whole picture here is other galaxies, and most of them are at an immense distance, around 12 billion light years now. So it seems to me that space travel for humans is not in the cards. I think we are even at the best imaginable super relativistic spacecraft, we're really not going to get anywhere in this universe as far as exploration goes. So, but you know, we shouldn't be sad about this. One way we can explore the universe is by exploring a simulation. And a simulation of the universe, we don't have to be constrained by relativity. We can move freely through the universe. And I just want to show you one of these simulations. This is the Euclid flagship simulation. It's the world's largest cosmological simulation that's so far been performed. And along with my friend and colleague, Doug Potter, we simulation about in the summer of 2016 on the Pitt-Stein supercomputer here in Switzerland. And what you see here is basically the structure of the dark matter. This kind of network-like structure is the structure that the dark matter forms. So you're only seeing dark matter in this picture. And it's a thin slice through the simulation, so it's, otherwise it would be confusion. And in the center would be located the Earth. So we're located in the very center there. And if we look at the very far right side, that's 10 billion light years away. So those Hubble Deep Field galaxies are just a little bit further to the right. And their light is emitted and travels toward us, as the arrow shows, encountering this structure of dark matter in its journey. And while it encounters it, it doesn't just pass through the dark matter, it actually gets slightly deflected and distorted by the intervening matter. And this effect we call gravitational lensing. This technique is actually how we will measure what the dark matter is. Even though we can't see it directly, we will use this distortion of the distant light of those galaxies to measure what's in between. And this satellite is the Euclid Satellite, which will be launched in 2021 on a Soyuz rocket, and will serve about 6.5 years. We'll be taking data, and basically what its mission is to take basically a Hubble Deep Field over most of the sky. So instead of just one tiny little patch, we will have a picture covering most of the sky with something like 50 billion galaxies in this image, if you can imagine it as a single image. And we'll be not so much interested in the actual galaxies that we see, but in those tiny distortions that are present and which will tell us what the intervening dark matter is. Now, I'm an astrophysicist, but I don't work with telescopes or their beautiful data and images. I'm also not a pure theoretical cosmologist. What I spend most of my time doing is programming and using supercomputers, as Valentina already sort of said. So what I'm showing here is the machine that ran that big simulation. This is Pitt-Stained. It's located at the Swiss National Supercomputing Center in Lugano. And it is actually the third fastest machine in the world. And I think that's pretty amazing. We're talking about niche things. This is an incredible niche that Switzerland has. There's only 2 machines in the world in China faster than this machine. It's faster than all US computers. And we have it here to use, which I think is a pretty special thing here. And it's capable of about 10 to the 16 floating point operations every second. And this is a nice tool if you want to run simulations. So so I spend a lot of time thinking about how to make calculations run faster on such machines. For example, the simulation code that we use, you could write your own cosmological simulation code in about 20 lines of computer code. And the code that we've created, which is called PKD-Graph 3, is basically doing the same task, but it's doing it much, much faster. And it's about 54,000 lines of C code. But effectively, it's doing the same job. So a lot of effort is invested in programming these machines. Now, if we're doing such a simulation, we have to consider what's involved in the universe. Basically, we're following gravity in these calculations, and we have to know what the universe is made of so that we can calculate how that stuff interacts on itself in some sense. So this pie chart is actually shown in probably half of all astrophysical talks. I've chosen a kind of a pretty version here. But the beauty of this pie chart is not the nice graphics, which are indeed quite nice, but it's sort of a triumph of modern cosmology that we actually know the stuff that the universe is made of. We have all the normal matter here. This is everything made out of quarks. Mostly it's hydrogen and helium. we have dark matter, and we have the dark energy, which I'll talk a bit more about. So it's quite a nice chart with about this is about 5%, which is all of the stuff we really know about. But it has a problem, and namely, the problem is this, and this. What I mean by that is that basically the normal matter, let's start there since it's something we're familiar with, it shouldn't exist at all. So in the early universe, there should have been an equal amount of antimatter and matter. And as the universe evolved after the Big Bang, it should have all annihilated and turned into photons. So we should actually, this should all be a sea of, this should just be a sea of photons that we live in and not have any matter at all. Dark matter, clearly we don't know what it's made of, but for sure it's not something that's explainable by standard physics, and it does seem to require an extension of physics to really encompass some matter of this type. And dark energy, probably the most mysterious of all of the components, which was seen as an accelerated expansion of distant supernovae, came as a real surprise to astronomers and physicists when it was discovered. I don't think anyone expected it to be a real component, but it has confirmed itself in many observations, not just from the supernovae, but that there is this huge fraction of energy, which instead of like normal gravity pulls things together, this stuff actually pushes, it causes the universe to expand more rapidly. So basically, you know, we have all three components of this chart are not explainable by current physical models, and furthermore, the sum of this entire pie chart here, normally you think of this as a percentage, that this would be 100% all the way around, but actually has an absolute value. That is, if the value that's required, that when you add these things up, is actually exactly 1, where 1 is that the universe is exactly flat in its geometry. And it actually, the fact that it adds up to almost exactly, as far as we can tell, exactly 1, seems like a colossal coincidence. And it seems to indicate that something in the early universe, during the Big Bang, kind of tuned it to be flat, the universe. And we call this process inflation. And again, it's something, although we think it happened, we don't know any of the details about it. So exactly how it took place is still a mystery. Okay, so thank God I've got that out of the way. Now I can get on to a little traveling. So we're here. I want to follow basically the light of a distant galaxy 10 billion years ago, much like what Euclid would see, and follow it to the present. So we're sort of like riding along a photon, but we're not being affected by any relativistic distortions or anything. So here we are. This is the structure already 10 billion years ago. You can see it's already quite structured, the dark matter. We have the highest density portions are in sort of yellow gold. Those are the dark matter halo. They're the halos. They're the highest concentration of matter. And inside each one of those would be one or more galaxies. So they're sort of the homes of the galaxies. Between these high concentrations, we have these dark filaments, and then we have very empty regions of the universe, so-called voids. So if we move a little bit further on, we can see things have evolved a little bit. The voids have become more pronounced. The universe has evolved. And we can see that some of these halos are starting to concentrate themselves. So instead of, they're still individual galaxies, but they're starting to come together. And we'll see this process will continue. And at some point, we will form galaxy clusters. And you can see a galaxy cluster concentration of mass here, for example. Now, I'd like to just stop here and just show you two galaxy clusters. The first one is this one here, and the galaxies in the cluster are sort of the reddish yellow galaxies that you see, but you can also probably notice something very strange. You can actually see the distortion that I was referring to, this gravitational lensing. You can see the distant blue galaxies being distorted in sort of tangential arcs about the center of the cluster. And by measuring these distortions, we can very precisely say how much mass is actually there in that cluster, how much gravitational mass is there. And it's way more than is in any of the visual parts. So if I add up the mass in all the galaxies, we're nowhere near to the total mass that would cause the light of distant galaxies to bend like that. And the second cluster I want to show you is a very famous one called the Bullet Cluster, which is probably the best evidence that dark matter really does exist in the universe. I mean, there's many indications of it, but this one is really hard to put away or to explain away in some other way. You pretty much have to have dark matter to make this work. And what's happening, what you're seeing here, let's ignore the blue and red for the time being. Just look at the visual light, which is the galaxies. You can see that they're concentrated in sort of two groups, two clusters of galaxies here, which are very close to each other. In red, you're seeing X-ray emission. So this is light in the X-ray radiation, which is emitting. And this is where most of the normal matter is. So all of the normal matter is not in the galaxies, but in this strange diffuse red stuff here, which is actually the X-ray gas. It's the hydrogen and helium. And finally, in blue, you have a picture of the lensing mass. So this is the mass that we would infer from those distortions. And it's most of the mass in this picture. Now, what's happened here is that these two galaxies this one has shot through the other one, therefore, hence the name Bullet Cluster. And the galaxies have passed each other without touching each other. They've more or less just gone through each other as you might expect them to be able to do. The gas, on the other hand, has gotten held up in the middle. In fact, it's gotten shock heated, and that's why it's emitting so many X-rays. It's very hot now because it's being crushed together by this collision. And the dark matter, strangely, has seemed to follow the galaxies. So it's sort of passed through itself without shocking, as it should. And this is an interesting thing about dark matter, that it can more or less slosh through itself. It can basically pass through itself without noticing, and without any resistance. And I think this is a really impressive observation. Okay, so let's continue the journey to the present. Now we can see the galaxy clusters are still growing. We've got more clusters growing. Their era, which I've called this the galaxy cluster era, their era is ending here at this point. And the reason why it's ending is because dark energy is starting to accelerate the universe. And what's happening is that there's two effects. Gravity is trying to pull mass into the cluster, and the universe is expanding. And because it's accelerating in its expansion, it's starting to pull mass away from the clusters. So they basically, their growth is now being stopped. And so this era is now ended. And basically clusters remain at the same size. And now we enter what I like to call the void era, where the only thing growing now are the voids. And this process continues. The voids get ever larger. And this is now, we're at the present. You can see we have nice, large, void-like structures. They will continue to get bigger. We have filamentary separating, these voids separating these filaments and the clusters. Now, that's very nice, but what I wanted to stress to you is that we can change the properties of the dark matter and the dark energy, and we can change the outcome of the simulation. So maybe the voids are slightly smaller or larger, or if we change another parameter, the galaxy clusters will be slightly more massive or less massive. And hence, the distortions that Euclid, the satellite, would see would be slightly different. And what we have to do then is to compare our simulations to the observations. And when we have the matching, then we have determined a property of physics. So that's basically the program of what we want to do. Simulations are incredibly important for the Euclid mission. Without them, the whole mission sort of, in my thinking, doesn't make any sense. You actually have to do the simulations to compare to the data, and you have to use supercomputers because there's no pencil and paper theory which can accurately describe that structure that you see on the screen there. Okay, so I'm almost done. We've sort of ignored one very important dark actor, and that's the neutrino. And neutrinos, we know they exist. We can measure them. There's 3 different neutrinos, 3 different flavors. And we also know that they have a mass now. Since 1998, it was determined in this detector here, this is Super Kamiokande in Japan. It's normally filled with ultra-pure water. So this is in a servicing. You can actually take a picture at this point. But this detector determined that neutrinos have a mass. It must be a very small mass, but there is a heck of a lot of neutrinos. And so they have a non-negligible effect on the outcome of the evolution of the universe. And this will be, I think, one of the very first things that Euclid will be able to determine, which is impossible for the particle physics detectors to determine, and that is the mass of the neutrino. We know it has a mass, but we just don't know what it is. And it's really important because the fact that neutrinos have mass at all is also another violation of present-day standard physics, let's say standard fundamental theory of particle physics. So they shouldn't have a mass, they should be massless, but they do have a mass, and we would like to know what it is. So, so like the other actors, these 3 actors, we have neutrinos, dark matter, and dark energy. All of them violate fundamental physics in some way, and really are setting a pathway for us, what the future of physics should be. We have these amazing examples of signs that we actually don't understand things very well. And I think this is what makes studying the dark cosmos so exciting right now. Thank you.
So thank you, Joachim. And we are finally at the break now.
Oh, I'm good. Just about good. Yep. Thank you, Joachim. Wonderful. It's interesting to see what the theories are going on behind, so that we can figure out what we should practically try to spend our time and effort doing. So we are running very late. All the speakers have been so interesting that they continued speaking, and so we're a little hurried for time. And what we'd like to do now is explain to you a little bit about the rocket competition. So to help run the competition, I'm going to introduce Yuri Gagarin. He's the president of Argos, which is the Advanced Rocket Group of Switzerland. So, do you want? I'll set up the video. Yeah.
Thank you. Oh. So yeah, I'll tell you a few words about Argos, and then we'll go right away to the competition, not lose much time on Argos. Some may have noticed we have put up a rocket and some flyers, so those interested in what we are doing, we are glad to tell more about on the private base. Just one word or two. Argos stands for Advanced Rocketry Group of Switzerland. We are amateurs doing anything, let's say, from simple model rockets up to quite ambitious amateur projects going to several kilometers altitude. So that's one typical rocket we are exposing there to give you an idea. But the reason why I'm here is really to help you through this rocket competition, matchstick rocket. That's actually the smallest rocket I've ever built. And it's quite fun. It will be a little bit of a challenge. We have a video to explain the assembly of the rocket. Those who are seated have received an envelope with all the parts prefabricated. Sound is missing.
Yeah. No.
And now?
Okay. Okay. So, all right. So. usually stuff in there, and I'm not talking about the match head, I'm talking about the super glue. So to avoid spills and messes and accidents, skin-to-skin contact, what we recommend you do is right now, pull out the super glue, careful not to drop any of the other contents, and we'd like you to open the packet and pierce the top. Without squeezing the tube, please pierce the top first. This means that when you want to use it afterwards, it won't come gushing out.
And there is also someone without the super glue.
If anybody doesn't have, don't worry,
Yes.
there's more than enough super glue to go
Yes.
around.
Yeah.
So
Okay.
you'll be able to ask anybody else who's holding one. You only need a half a drop, so there will be plenty. Okay, so everybody's pierced.
Yeah, just through the,
Yes.
the distributor on.
If you use the red lid, you turn it upside down and push it onto the tube.
Right.
I think
You'll
they need
pierce it.
some light because
Yeah,
they
they
cannot.
need
Oh,
some
yeah,
light in here.
so
Can we
maybe
have
can we
some
have
more
some
light?
light?
Here. I think.
Anybody?
So now it's
Anybody's
not
trying?
It's not
possible.
possible.
Okay, so we have
So
to
we'll
move.
have light after.
Okay.
Yeah.
All right. So, do you want to walk us through how to
Yeah.
make the and I'll make one right in front of you here.
Yeah. Just one thing up front. Don't use the glue on your lap. We have a table outside with plastic on it. Don't spoil your clothes with that stuff. So now the assembly. You find a dowel and the match head and a piece of aluminium foil inside your package. So all of this has already been done. We may have to shorten it. That has been cut. You see a green line indicating the corner where you have to start. So this is the forward end, the green line, and then you wind it up from the wide side towards the small side. Yeah, and the pointy end of the stick is going in. You roll it up tightly, and then you have another piece, a small square aluminium. Maybe you pause it for a second while people identify all the parts inside.
You have only one
don't do it
possibility.
right now. You have after with light, you have more time. Just understand how it works. So you wrap it up tightly, but you need to be careful that it doesn't stick on the dowel. It has to glide freely. Now you can go on with the video. Maybe we go back on the folding of this wing because this has possibly been missed. So this is a small square that you fold twice diagonally and make fins out of it, as you see now. It looks easier than it is, actually.
It's easy.
And then that's where the glue comes in. On the end part, you need to put some glue to attach those fins to. But you can do that outside, as mentioned. And then we have, this part is not for you, we have ready-made rocket launchers. But you see how it works if you want to replicate and try some more at home. So we have 4 rolls of ambitious 50 meters of thread to measure the maximum distance. I would be pleased if I need more than 10. What we will do, the procedure outside will be you queue up behind the launch places. You hand over the rocket that's installed on the dowel. We put it in the launcher, we launch it for you, we take the distance. If the distance is further than the current leader, we take your name. And at the end, we determine who won. So we have the video running on a loop, so you can see and revisit how it is done. And then as soon as you're done, we are outside. And if you have questions, we are around as well.
So, thank you, Jörg.
Welcome.
So we have only 30 minutes. So that makes it until 1:15 that we'll return. And you'll tell us who the winner of the competition is. And just for a couple of tips, I've made plenty of these myself and had lots of fun shooting them off my balcony. They are a little bit random. Sometimes they work well, sometimes they don't. I've tried with double match heads. It doesn't necessarily make it go any further or more successful, so I recommend just one match head. You'll find that the match head is stuck in the envelope with a small piece of tape. There are spares of anything for those of you who accidentally tear the foil or anything. Now, some tips are when you roll it, keep the green part, the green side together, and roll it as tightly as you can around the skewer so that it can still slip on and off, but otherwise as tightly and neatly. And at the tip, you just squeeze it with your fingers in several directions. You can twist it a little bit. Some will misfire, some will shoot literally 10 centimeters, and others, you'll be stunned how far they go. I mean, really, I couldn't measure mine because they went so far.
We'll do our best to find them actually outside now that it's quite dark, but we'll see.
And with the super glue, you only need the tiniest dab on the, the spiral part. To be honest, I think that the fins are just there for cuteness.
No, it takes them to fly straight.
It does?
Yeah,
okay.
Otherwise it would. So have them true and straight. That's important if you want to win.
Great.
So you have one possibility, not more. So let's go.
So let's have fun.
Поехали.
Okay, see you back at 1:15.